Okay, so hello everyone. Welcome to this reading room talk on how does information work, with the clickbaity subtitle of 1 bit does not equal 1 bit. So this is going to be a talk on information theory, and information theory is about understanding the movement and transformation of information through mathematical and physical laws. And ultimately, it's concerned with answering two fundamental questions. The first of which is, how much can you compress data? Right? So, or another way of putting this is, what is the entropy of a piece of data which determines how much we can compress it? And we call this H. And it also is concerned with the second question, which we won't address in this talk, but we could do at a later date, which is, at what rate can you reliably communicate through a channel? So this is, which might have a capacity, and yeah, we will explain the first one and answer that today. So, why do we care about information theory? Well, basically, it's widely applicable, right? And some of these might seem quite obvious, such as compression and communications and networking. But then it also extends to things like data-oriented design, which is becoming increasingly popular in the games industry, in allowing us to structure code in a way which is more efficient and more maintainable. But it also extends to things like machine learning, computer vision, and computer graphics. And also outside of computer science is relevant from subjects like linguistic to physics and how the universe itself works. And we will go into some of these at the end. So, what does this talk contain? So we'll go through some foundations. So we'll introduce the concepts of information theory. We will go into Bayesian probability. We will cover entropy. And then finally, we will look about source coding and how to construct codes. Then we will look at compression and how compression works. And then finally, we will relate this to a whole bunch of different fields. And it's worth pointing out that this presentation is not mathematically rigorous. The arguments I'm presenting are going to rely on intuition and not formal proof. And the goal here is to be user-friendly, not technically precise. And this is going to be at a very high level as well, with a bit of depth early on. So, foundations. So, it's worth pointing out, and this is the core part of information theory, which is I find interesting, which is that data is not the same as information. And there's a bit of intuition about this, right? If you buy a new hard drive, it's always, it might have a terabyte of data on it when you buy it. The amount of data on it is never going to change through the course of its lifespan. But you do intuitively understand that when you buy a hard drive, it's not going to have any information on it. And then there's also an interesting, question that springs out of this is there a difference in terms of the information content between a zero initialized hard drive and a randomly initialized hard drive? And the answer to this question is yes, there's a big difference, but the fact that the meaningful difference to us might not be very significant is also of interest for later. So, the thing about information theory is that probabilities matter. And in, kind of to provide intuition for this, right, is if I tell you now that my name is Tom, to most of you, you are expecting me to say that my name is Tom, which means that by telling you that, the amount of information I'm transmitting isn't very high. However, if I were to tell you that my name is now, I don't know, Jeff, then that would be more information because you would learn something new. Oh, I've got a new name. And even though I'm using the same amount of data to transmit that information, those two pieces of data would be containing different amounts of that. So intuitively, this means that the less probable an event is, the more information it contains when it happens. And I find that really fascinating. And we'll go into the maths behind this now. And this comes to the really interesting part, which is one bit of data is not one bit of information. And I'll expand on what this means later. But essentially, we use the word bits to describe units of information in the same way we use bits to describe units of data. And although they are fundamentally different units, they do have links to each other. And what I can say now, for example, is that one bit of data contains one bit of information if and only if the probability of that bit being either 1 or 0 is exactly the same, so a half. And this will all be revealed in due course. So the next bit is that knowledge affects information. So intuitively, past events affect the probability by which we predict future events, right? And if I bring this sentence up, the reason you can read this sentence at all is because your brain has already, built up, has learned the probabilities of what the missing letters could be and fills them in automatically. And actually, I find it incredibly awesome that our brains can run this super hardcore Bayesian inference stuff all the time without us even realizing to fill in data from where we would expect that redundancy to exist. And we are actually quite good at reconstructing data or even information when it might be missing based on what's probable. Yes. So let's delve into some probability then, so we can actually start dealing with some actual maths and going into some working with some concrete numbers. Bear with me for this part because I do go over this quite thoroughly. But this is really important because information theory is defined by probability. And as we will discover, information is the same as entropy is the same as randomness. So let's go over the basics. So just introducing some syntax. When I write down PA, it means that for some event, let's call it A, PA says how likely that event is to occur. So in other words, PA is the probability that an event A will happen. So hopefully, the probability I will say during this talk would be low, but I know that the probability of me saying is high, it's 1, and also that doesn't therefore carry much information. So basic syntax. When I write PA, B, we are just talking about how likely are both events to happen. And hopefully the probability that I will give this talk and swear at the same time is low. PA given B. So this syntax is describing how likely is A to happen if B has already happened. And this is known as conditional probability, right? So just to kind of give an example on this, is the probability of me swearing, given that I've stubbed my toe, is going to be very high. And you can kind of already see why this might be important for information theory, because, especially when it comes to compressing files, the information that the probability of information that gets delivered, further on into a compressed file the probabilities of that information will depend on what came before, right? Or with words as well. Human speech has a lot of redundancy, so when I'm talking, the words that I will have to use to complete a sentence and the probabilities of me using them will depend very much on which words I use to start a sentence, for example. Cool. And now this brings us onto some rules, right? So the probability that both A and B will happen is the same as the probability of A happening if B happens multiplied by the probability of B happening. And then also that's the same as, if the probability of B happening if A happens multiplied by the probability of A happening. So just to provide some intuition for this stuff is if we're trying to describe the probability that Alice will both buy a hot dog and buy some ketchup, well, if we know how likely Alice is going to buy some ketchup if she's already bought a hot dog, and we know how likely she is to buy a hot dog, then by taking how likely she is to buy the hot dog and how likely she is to buy ketchup if she's already bought a hot dog, we can multiply those two numbers together, and we then know how likely both are to happen. And then we also have the sum rule. So if, let's say, we want to work out the probability that some event A will happen, and we know the conditions that could cause that to happen. So we know we have, let's say, events B that could we know that A will happen given these different types of B. Then by summing all of those together, we can calculate the probability that A will happen. And just to give some intuition for this one, so if we're trying to work out the probability that Bob will beat Alice at chess, right? If we know the probability that Bob will beat Alice at chess when starting with blacks, and if we also know the probability that Bob will beat Alice at chess if starting with whites, we can then, add those two probabilities by the probabilities that Bob will start with either of those colors, and we will then know the probability that Bob will win at chess if they were to play a game. And then this brings us to Bayes' theorem, right? So if you remember, we introduced a product rule before. And if we rearrange this a little bit, we can get this really nice equation. And I love this equation because it has some really interesting properties. And it basically lets us, if let's say we have some event B, and we know how likely that's to happen, we have some event A, we know how likely that is to happen, and we also know how likely A is to happen if B is going to happen, and you want to work out the opposite, then this equation, we can just plug in those numbers and it gives that to us. So let's give an example to kind of show how this equation can reveal how unintuitive our understanding of probability can be. So imagine that, this example might be a bit close to home right now, but imagine that there's a 90% accurate virus immunity test. So it's a test you can take and it will tell you if you're immune to a virus. And if you have any, you are immune, it will give you the correct answer 90% of the time. And if you're not immune, it will give you the correct answer 90% of the time. Now, imagine that in real terms, we know that 1% of the population is actually immune to the virus, right? So we know that only 1% of people are immune to this specific virus. And we want to know, if you take the test and you get a positive result, what is the probability that you are immune to this virus? So we want to work out the probability of immunity given a positive test. Oh, actually, please write down your guesses in the comments. I just got told that the connection was poor for a second there. Is everything still okay? I'm just checking the comments. Okay, cool. Just grabbing my notes again. Cool, yeah. So just have a think about what you might think this number could be. So let's just write down the information we already know. So we know that the probability you are immune is going to be 1%, because that's what we said at the start. So that means the probability you are at risk to this virus is 99%. Now, if you, and now we want to know, the probability that this test is positive, and we know the probability that this test is positive given you are immune, and we also know the probability the test is going to be negative given you aren't immune is going to be 0.9, because this is what the success rate of the test means, right? If you are immune, it's going to give you the right answer 90% of the time. If you're not immune, it's going to give you the right answer 90% of the time. So all I've done here is written down those probabilities that we stated on the previous slide. And then similarly, we have the opposite for the chances that tests fail. So now let's apply Bayes to this. So the probability, so let's just work out so you can see Bayes, and we need to work out the probability of t before we can apply it. So let's do that first. So applying the sum rule, we know that the probability of t, so the probability the test is positive, is going to be the probability the test is positive given we're immune, multiplied by the probability of us being immune. And we also know that we're going to have to add the probability of the test being positive, given the fact that we're not immune, multiplied by the probability of us not being immune. So we're basically trying to work out under what two cases can the test be positive, what are the probabilities for those two cases, and then we're calculating those and adding them together to get our final probability, which is 0.108. So, are you immune? Let's do the maths. We've got these numbers. Let's plug them into the equation. And the answer is less than 10%. So if you have this 90% accurate test, which tells you whether you're immune to a virus or not, and 1% of the population are known to be immune, so we know that roughly 1 in 100 people are going to be immune to this virus. If you take this test, it's only going to have, and it tells you you're immune, it's actually only going to have 10% chance of being true. And that is why Bayes' theorem is important, because it's not what you think of when you think of 90% accurate test. And it's also why it's really important that these tests have incredibly high accuracy before they can be useful on any meaningful level. So, how does this then relate to information theory? So essentially, we can apply it recursively to let us use the latest posterior, so the latest information that's come in, and we can then use that information as a new prior to interpret the next set of data. And information theory is all about quantitatively analyzing the amount of information we gained by looking at the reduced uncertainty we get when we receive that information, and we do that using Bayes' theorem. And we're not going to go so far in depth into information theory as to use this to its extent, but hopefully you can see why this is incredibly important to the topic, and especially when we briefly cover some of the early interesting points about information theory and the maths there. So let's discuss entropy. So bear with me for now. This section is mostly going to be statements. It's going to be quite declarative. And then the intuition and tying this all together into something meaningful is going to come in the next section. And yeah, hopefully there'll be a eureka moment where this stuff all makes sense, because information theory is awesome. So if we have an event E, what is the information contained within that event? And there's an equation for this. It's very simple. We just say that the information of an event is just the logarithm of its probability, where the probability is a probability of that event occurring. And that's it. That's all information is. And you might notice that that will then produce a negative number because probabilities are less than 1. So we often just talk about entropy instead, which is the negative information. But you can kind of use the words interchangeably if you're not being, super strict or correct about it. NH measures uncertainty and measures information. And these numbers mean very real things. And we will come into that when we talk about coding. But yes, this is quite cool. And I like that it's how simple it is to just work out how much information an event contains. And we'll get an intuitive understanding of what that actually is very soon. So why do we actually use logs? So one very useful property the log function has is that it allows us to use addition where otherwise we would use multiplication. So if, let's say, we want to find the information associated of for two independent events, A and B, the probabilities of both those events happening together is going to be their probabilities multiplied by each other. So therefore, if we have that information already, the information for those events already, we can work out the total information of those two independent events by just adding them together, because of the way logarithms work mathematically. So yes, so going on to the next bit. So one of the things that's also really important is that we want to not just talk about the entropy of events, we also want to talk about the entropy of probability distributions, right? So if, let's say, you have a whole bunch of, if, let's say, you have a probability distribution where something can maybe take multiple discrete values, where the probabilities of each one of those discrete values all adds together to be 1, then we can calculate the entropy of that distribution by just summing the information contents of those events together. So just to kind of give an example of this, so like flipping a coin is a probability distribution, where it can either be heads or tails with a probability of 0.5. The probability of it being either of those is going to add up to 1, and that will have an entropy associated with it. And we'll go into a concrete example soon. So let's just go into some intuition then. So if, let's say, we have a bit, right, and we'll call this bit B, and let's say it has a probability of being either 1 or 0. And obviously the probability of that bit being 1 is going to be 1 minus the probability of that bit being 0, right? So there's two values here. And then let's just see how the entropy of this bit changes as we vary the probability it could be either of those values. So there's a graph here, and we are graphing the entropy of this bit as the probability that this bit goes from 0 to 1 equals 1. So just to explain this intuitively, so if we know that that bit is always going to be set to 1, then that bit doesn't have any entropy. It has no information because it's always going to be the same value. Similarly, if that bit is always going to be 0, then if you find out that that bit is 0, that's telling you no information because it's always going to be that value. And then what's interesting is as the probability tends towards the middle, as the probability of it being either 1 or 0 becomes 0.5, so it could be either with equal probability, then you can see that entropy maxes out at 1. And it's only at the point at which we can make no predictions about what this bit might be with anything beyond it could be either 1 or 0 with equal probability that that bit has maximal entropy. And also, if you then were to inspect that bit and find the value of it, you would be transmitting the maximum amount of information that a bit could contain. And this is why we talk about data in terms of bits and information in terms of bits, because ideally we want to make sure that our bits of data, in some contexts, such as when dealing with compression, we want to try and ensure that our bits of data always contain one bit of information. And we do that by maximizing the randomness of our data through compression. And that's jumping quite a bit ahead there. And we'll build up to that throughout this presentation. So that's all we're going to go into with regards to basic entropy, and we'll be looking at coding next. And there's a whole area of mathematics with regards to dealing with entropy under different conditions and with different kinds of entropies, such as calculating the entropy of independent random variables and conditional ensembles. There's also chain rule. You can also reason about the mutual information two variables might have with regards to each other. And then there's things that mathematical concepts such as the Kullback-Leibniz distance and Fano's inequality. And unfortunately, there's not enough time to go into them this time. But if you are interested in this stuff, these are some good words to Google. And I also have some references at the end of this presentation, along with further links, where you can find this stuff as well. So let's talk about source coding. And this is going to be the bit where we take what we've learned about entropy, how many bits does a probability distribution contain? And we talk about, well, how can we make this meaningful and ensure that we encode our data so that one bit of data will equal one bit of information. So imagine Alice is sending Bob 4 letters, A, B, C, and D. So she's just spamming Bob with letters, but there's a probability distribution as to which values these letters can take. So let's say the probability that she'll send an A is 1/2. The probability that she will send a B is 1/4. The probability that she will send a C is 1/8. And the probability that she will send a D is also 1/8. And that's an example. I actually used a random number generator for this with the correct probability distribution. She could send DA, DD, BB, AD, AA, BB, AA, CB, DA, BC, AAA, DC. And that, it's a bit gibberish. Alice and Bob have very weird interests, but, it's up to them what they do in their spare time. But how much information is Alice sending Bob? And that is what we are interested in as normal people. So how would we do this then? So if we're dealing with computers, we are going to be wanting to encode this data as binary, most likely. Or, well, that's the only option, really, unless you've got some really interesting CPU going on. And a naive code might look like something like this. We have 4 letters, so we use 2 bits per letter, right? So we just say A is 2 zeros, B is a 0, 1, C is a 1, 0, and D is 1, 1, right? And then you can imagine a binary stream of these 1s and 0s, and we can easily, convert them back to letters if we need to. And this code has what we call a fixed code rate, right? Where the code rate is simply describing the mean number of bits used per symbol, okay? And in this case, it's very easy to work out. because we are always using the same number of bits per symbol. So we know that the mean number of bits per symbol is always going to be 2. So our code rate is 2. And we call this R. So let's then compare this to the entropy of the system. So remember, previously we introduced this equation for calculating the entropy of a probability distribution. So let's just plug in the numbers. This is going to be the entropy of A plus the entropy of B plus C plus D, which is going to be these numbers. I've just plugged in the logarithms for you, so you don't have to do the work there. And eventually we get 1.75, and that should actually be 1.75 because the negative would invert the negative logarithms, and that's a mistake on the slide, I just realized. So what does this actually mean? So this tells us that every time Alice sends Bob a symbol, she's going to be on average transmitting 1.75 bits of information. Okay, so then what does this tell us about our encoding, the code we made before? Well, that sends 2 bits per symbol on average. And if we know that each symbol contains on average 1.75 bits, it means that our code is inefficient, to some degree. And one of the things that's really awesome about information theory is even with the really basic stuff we've covered so far, we can get a precise number for how inefficient our code was. And it's, about 87 or to 88% efficient. So we could do better. We could transmit the exact same amount of information. We could get Alice to send Bob those symbol sequences whilst using an encoding which would use less bits in total to send this. And we should be able to get about a 12% efficiency gaining here. So it's worth giving it a shot. So how would you do this? So I'm just going to Blue Peter this and kind of provide the solution from on high. But now imagine a different coding system where instead of having a fixed number of bits per letter, we use a variable coding scheme where A is going to be 0, B is going to be 1, 0, and C is going to be 1, 1, 0, and D is going to be 1, 1, 1. And if we're going to look at the likelihood that each one of these symbols is going to appear, we can kind of work out the coding rate, right? So the coding rate is going to be the probability that A is going to be sent multiplied how many bits we'd have to send if we send an A. And then we're going to have to add 2 times the probability that B is going to happen. And the reason for this is that, every time Alice sends a B, she's going to be sending 2 bits. But we then multiply that by how likely that is to happen to work out, how many bits are going to be sent on average. And we do that again for C, and we do that again for D. And then if we look at this coding rate that comes out, you'll see that it's 1.75. So we've managed to create a coding scheme where by using these codes to encode our symbols, when Alice sends Bob a bit stream, that bit stream is going to be using roughly 1.7 bits it's going to be using exactly, in the course of time as the universe tends towards infinity. The amount of bits used to encode each symbol is going to be 1.75. And as I said before, and I apologize for this code was plucked out of thin air, but it does have some important properties that make it work. Firstly, one of the things I'm going to say now is that if we try to find a code with a lower coding rate, it will be impossible to do so without losing information. And this is a hard law of information theory, where you can't write any coding scheme with a lower coding rate than the information you're trying to encode in that coding scheme just isn't going to exist. So we know, because we know the entropy of the probability distribution, and we know the coding rate of this, and we know that they match each other, we know that we have found the perfect code for transmitting this information. And that's really cool. We know we can't do any better. Another thing about this code, which is not directly linked to information density, is that it's instantaneously decodable, which is also a useful property. So what that means is that none of the encodings for any of these symbols is a prefix for another symbol. So as you can see here, we use different numbers of symbols for different numbers of bits for each of these symbols, right? But for example, none of these symbols start with the 0 except for A, because A is only one symbol long, and that's the symbol it uses. And this is known as the prefix property. And that's something that we want to have with these kinds of codes. And that these kind of things can be easy to mess up in more complex situations. And there are systems for constructing codes like these, which we unfortunately don't have time to go into, such as Huffman trees. Yes. And just to kind of summarize this all together in Shannon's source coding theorem, is that you can compress a stream of data with entropy h into a code whose rate r approaches 8 in the limit. But you can't have a code rate r less than 8 without information loss, which is basically saying, getting r to be as close to h as possible is going to be as much as you can possibly compress a stream of data, but you can't go beyond that limit. And then finally, just to kind of talk about, where compression gets more interesting, right, is that here we worked with an incredibly simple case where we knew the probabilities for these symbols up front and the symbols were fixed, right? So the probability of Alice sending an A once wasn't going to be affected by what she might have sent before. And obviously in the real world, with typical communication streams, the symbols we send in the future can be affected by stuff we send in the past, right? And it can be very dependent on context, right? Like photos will all have very similar patterns of data in them, whereas cartoons will have very similar patterns of data as each other. And you can kind of imagine that, right? Like a photo of a tree in the natural world is going to be lots of continuously changing colors. You're not going to get any high frequency changes or anything like that. Whereas a cartoon is going to be, block colors. And these two types of data, if you know ahead of time what you're going to be dealing with, you can develop context-specific compression strategies to deal with those appropriately, right? And this means it can depend very much on the recipient how far you can compress things, right? If you can, for example, if you and a friend are going to be sending each other selfies of each other every single day, and you want to maximally compress the selfies you send each other, you could probably make an incredibly good compressor that is very good at compressing selfies of your own face, right? But obviously that requires transmitting all the information about your face needed to compress that data ahead of time. So there are trade-offs here, and the probabilities are not fixed, they're dynamic, and trying to figure them out is basically the entire battle. And good compression systems are as much about trying to accurately discern the entropy of each symbol for the target recipient as it is anything else. So if you want to read more about this stuff, I'd recommend Googling these terms: Huffman codes, Huffman trees, the Kraft-Macmillan inequality, which deals with how you can construct instantaneous codes and the limits to how they can exist. One of the things that's really fascinating, wait, give me a sec. one of the things that's really fascinating about this is that you can code an infinite alphabet this way. So if we have an infinite alphabet, where there's just an infinite number of symbols, if the probability distribution is similar to what we look now. So if, let's say, the probability of A was a half, the probability of B was a quarter, the probability of C was an eighth, and we had that for an infinite alphabet, we could actually encode that alphabet while still being able to only send 2 bits per symbol on average. And that's an incredibly fascinating quality. And if anyone's interested in that, we can go into that next time, how you can prove that, because it's really cool. And then finally, Markov chains are really interesting to read into, because these let you encode probabilities using state machines, such that the probabilities for symbols can vary based on which symbols you've seen before. So yes, let's jump onto compression then. And this is going to be much more generic, much more high level, but hopefully with the intuition you've got from the previous sections, you can get a feel for the kind of mathematics that might be involved here and how compression actually works. So coding covered how we could have different ways of coding the same data to make it more or less efficient, but then how does this apply to general purpose compression? So compression is hard, right? We basically want to find out what's the probability. We basically want to find out as accurately as possible what's the probability that the next bit in the sequence of data we're trying to compress is going to be a given value, given every bit that we've seen previously. And we need to do that for a target recipient, right? Where, we need to do that in a way that they'll then be able to decompress that data whilst under the constraints we have, giving them the information ahead of time that we can, but that may be more or less generic depending on the context, right? So context is key, right? So are you trying to create a general purpose compressor, right? Like, are you just saying, I'm trying to make a compressor that just tries to compress the kind of data we see on computers in general? And that's a hard problem, right? Because you get image files, you get text files, you have source code, you have language, you have different languages, you have photos, you have pictures, you have music, you have films. So the how effective your compressor is going to be more limited in this case, versus if you're going to be compressing images, versus if you're only going to have to deal with compressing cartoons, versus if that you're only going to be compressing Simpson characters, right? If you're going to be compressing Simpsons characters, you're probably going to encode the color yellow in as few bits as humanly possible, because that's what you're dealing with. So what kind of compressors can you get then? So we're just going to go into some few high-level patterns. So the first one is the dictionary method, which is a general purpose type of compression, which just assumes that patterns are going to be repeated within the same source of data. So basically, every time you find a new word, you put it in a dictionary, and the next time you just encounter that word, you refer to that dictionary entry. Super simple, right? And that works really well for things like human speech, or human text, rather, where the word the comes up incredibly frequently. So if you can just point to a cheap entry in a dictionary saying, this is the, rather than encoding the bytes for the directly, you can get some incredibly efficient results. But obviously, constructing the best dictionary is hard. And a lot of these dictionary methods have to constantly destroy and reconstruct their dictionaries based on new probabilities. And, especially with data where you don't get these kinds of repetition, they can end up actually performing worse than just leaving files untouched. Cool. And then we have run length encoding, which is incredibly simple. We just assume data will be repeated. And we just count the number of repeated bits or bytes, and then just store that in the first instance of them. So just a really simple example here. if we had 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, we could just say that's 11 noughts, 4 ones, and 3 noughts. And usually you wouldn't do this at the bit level, you would do this at the byte level or word level to be more efficient. But this, if you know you're going to be dealing with this kind of data, this can be one of the most effective forms of compression you could do. And it's really simple, right? Another use case is learning compressors, right? You can train a compressor for a specific use case. And a good example of this is network compression. So Rad Game Tools have a compressor called Oodle Network Compression. And what you do is, as a developer, is you play your games internally. You tell the compressor that you're playing these network games, and it builds a dictionary of what the packets are likely to be ahead of time. And then when you ship the game, every client will have a dictionary of packets and their probabilities and what they're going to send. Then instead of having to send full packets over the network to other clients, you can send these dictionary lookups essentially. So it's a type of dictionary compressor as well. But this you can kind of start to see now how this might start branching into topics like machine learning. And that's where the lines start getting blurry and interesting. And then finally, we have lossy compression, right? So we talked before about how it was impossible to encode things with a rate r less than the entropy of the distribution, but sometimes that's okay. And sometimes you do want to throw away information, and lossy compression works really well for images and videos, where the way human vision works, our eyes tend to naturally discard a whole bunch of information from the raw images our retinas receive anyway, so why not just do that to an image? And lossy compression is all about achieving coding rates which are much slower than the entropies of our distributions we're trying to compress, but doing that smartly so as to discard less interesting information to a particular end user. And for example, JPEG uses fast Fourier transforms to achieve this. And this is a broad topic, and it is an entire talk or 2 or 3 or 4 on its own that can be expanded on at a later date. And there's a happy cat in the background. Well, it was a good excuse to use that more than anything, really. So that's everything on compression. Very broad, very high level. Hopefully this gave you enough of a window into the topic to kind of motivate your own learning and give you an idea of how compression can work. And then finally, we're going to round this off with how information theory can relate to a variety of different topics in computer science. So obviously, links to compression. I'm not going to go into that now. Communication and networking. Again, we kind of cover the compression side of that, but there's also the how do you reliably communicate through noisy channels side of information theory, which unfortunately we haven't had time to go into this talk, but that's an incredibly fascinating topic for next time. But then we have data-oriented design, security, machine learning, computer vision, and computer graphics. So data-oriented design, if you don't know what this is, I'd really strongly recommend watching this talk from CPPCon in 2014. It's especially relevant if you're a programmer or a games programmer as well. And in this talk, Mike Acton strongly advocates for engineering by focusing on solving the problem you have to solve and identifying that all software problems are ultimately problems of data transformation on a concrete set of hardware, right? So with modern CPUs, this means the focus is often on transforming data in a way that makes effective use of CPU caches, because those can so often be a bottleneck when we don't use our CPU cache effectively. And being able to reason about information density is a really important part of data-oriented programming, which actually came up in the talk, where he talked about the problem of trying to compute a single bit of data every frame. And every time you computed this bit of data, it would cause a cache miss, right? And he was saying, by computing data this way each frame is incredibly wasteful because you're having to do these cache misses each frame for something that you can maybe compute ahead of time when the data you need to compute these bits is already in the cache. But then when you throw information theory on top of that and work out how much information are we actually computing per cache miss, which is the actual kind of core measure of how inefficient is our code being, right? Then he found, incredibly low information per, like it was a fraction of a bit per time this cache miss was happening. And I'm not going to go further in depth here, but I'd strongly recommend watching this full talk. And if you've seen it before, I didn't quite get this section, I'd recommend giving it a rewatch because we've covered everything needed to understand the information theory side of this talk, where he actually does go into calculating Shannon entropy or using a zip file to work out the information density of data you're calculating, and then thinking about measuring the effectiveness of your computation in terms of information and not necessarily just pure data. We also then have security and encryption. So encryption is an interesting one, right? Where the goal is all about encoding information so that only someone, the intended recipients, can extract meaning from it, right? So from an information theory point of view, if we're looking purely at what we've already covered, when you send encrypted data, everyone is receiving the same amount of information, right? In terms of, how much you can compress that data, in terms of how you can reliably send it down the channel, the information is the same, but it's meaningful only to the intended recipient because they already have some other information that they can use to extract information from the transmitted data. But then even more interestingly, and this is where you kind of start teasing something a bit more fundamental about information theory out of the topic, right, is public key cryptography, where public key cryptography works, where you can encrypt information using a public key, but you can only decrypt information using a private key. And the private key is just the prime factorization of that available public key, right? And when you use public key cryptography to share information, what's really fascinating is that anyone, like in theory, if you have some encrypted data and you have the public key for that of that data, you actually already have all the information you need to understand that data. That public key is an encoding of the private keys and contains all the information you need to know about the private keys. And you have everything you need to decrypt it, but just because the information is there doesn't mean you can access it. And that's really fascinating, a bit of a tangent, but some parts of information theory deal with this stuff. And, it also then starts thinking back to physics and entropy and how the human brain works and how we need redundancy to understand things. But it's super fascinating and has many applications. Then finally, I'm going to bung machine learning and computer graphics together. So machine learning, right, is, so for example, we can talk about machine learning upscaling, and the only reason that works is because a 4 times increase in image resolution is not going to be a 4 times increase in information. So computing data every frame is incredibly wasteful, right? From a GPU perspective, if we're rendering 4K images each frame, but not having 4 times the amount of information versus 1080p image, what are we even doing, right? We're just, wasting resources there. And NVIDIA have solved this problem through machine learning, where they've, trained a neural network by comparing, by training it, by giving it low resolution images and some very high resolution ground truth data. So it can learn patterns as to what low resolution images then go to high resolution images. And that means you can have clean looking, high resolution looking data with the same amount of information. And then by feeding in historical data and motion vectors, you can even then extract information from previous frames such that even aliasing can be potentially avoided when you have information which is at a higher frequency than what your original low resolution images are capturing individually. And this is really fascinating and awesome stuff. And, state of the art as well. And then finally, let's just do a little experiment. So if everyone can look at this image, close their right or left eye, and then with the eye that's still open, so if let's say your right eye is open, look at the letter R. And then if you look at the letter R and bring your face so that it's about 3 times the distance from the screen as the two letters are to each other, you should see the other letter disappear. So my face is quite close to the monitor. I'm looking at the letter R, and the letter L has disappeared for me. And this is really fascinating because this is our brain, basically on the fly, constantly calculating, the probabilities of what information might go in a blind spot we have in the back of in our eyeballs, and going, well, okay, so there's a whole bunch of white. There's just a white background here, and I've got a blind spot here in the eye, and the probability that that's going to be white as well is going to be incredibly high. So I'm just going to fill in that missing data with white, but then actually it's got it wrong in this case, and a letter disappears. And what I find amazing is actually not the case where it breaks down like this, but just how amazing it is that our brain gets this stuff right so often that we don't even think about or notice it. And we have to construct these really contrived examples in order for it to work, in order for this to be revealed. And I don't know, it just blows my mind. It's amazing. And yeah, and just kind of tie this all together, one of the things that makes information theory hold a special place in my heart is the fact that it gives us a really interesting insight into the laws of the universe itself. We live in a world that, as far as we know, is constantly trending towards a state of entropy. And we have established, right, that no information is completely uniform and expected, right? And so increasing entropy implies that we live in a universe which is constantly having more and more information being added to it, which also implies that the next state of the universe isn't necessarily computable from the previous state, which is also incredibly mind-blowing. But on the other side of this, information needs meaning, right? And without meaning, information isn't really information. And in the march towards more entropy and towards more information, it's fascinating how it actually takes a lot of work to keep information around that is useful, right? Like random noise does not make useful information to the human being. And, with things like channel coding, where we have to try and stop, transmit data to be resilient in the face of corruption, we have to expend a lot of energy to just keep around a level of redundancy that's meaningful to us. And I find it fascinating that packing data into the smallest number of bits needed to store it takes work, energy, CPU time, and energy. And then unpacking that information requires work as well. And in fact, to have meaning, in order for things like images, text, anything to have meaning for us and for it to be useful, we need that redundancy, and we need to put in work to get the redundancy back if we have put in the work to eliminate redundancy and compress data. And I find it fascinating how a topic which, I don't know, seems to have such mind-blowing implications is also the foundation for efficiently distributing videos of cats around the internet. And you might be working out how to compress your cat videos one day, and the next day you're getting lost into the depths of the universe. So yeah, that's the end. I hope you found it interesting and it's piqued your interest for more information theory. There are links in the description of this presentation. I will share links and stuff in the description, and have a good one. Cool. And I'd just like to say special thanks to these people. Professor John Daugman taught this course at university, and that's basically everything I know about this topic. Thomas van Nuffel did an amazing title slide, Henry Ryder gave great feedback design and assistance. Alistair and AJ, were really good for ideas bouncing and feedback. And then finally, thank you to Hugh Bowles for organising this. And then finally, please subscribe to our YouTube channel. We have more talks available on computer chips and Git, with many more to come. And here are some videos you can watch in the future. And finally, here are some references for what I used during this talk. And if you're not at Electric Square yet and you're interested in a career here, and you've watched this online and found this interesting, please consider applying for a job. It's a great place to work. We have positions open for all levels of programmers, from junior through to technical director, including research and development roles. And we have studios across the world in Brighton, Leamington Spa, and Singapore. And see you next time.